comes in the meeting all rushed, throws a pile of fasteners, nuts and bolts on the table in front of me and says, how much am I paying you to treat these fasteners right now? And I said, I don't know, a nickel a piece, something like that. And he goes, man, you kidding me? He goes, you could have told me $25 a piece. He goes, every time I have to replace one of those fasteners for a galling issue, it's $1,000 in downtime.
Hello and welcome to another riveting episode of the Being an Engineer podcast. Today we have Scott Roberts with us, who is the North American Application Specialist at Bodycote, where he leads the team responsible for educating and promoting the S3P Kolsterising process, an advanced low-temperature diffusion technology that dramatically increases the hardness and wear resistance of stainless steels and cobalt-chromium alloys. With more than a decade in market development at Bodycote, Scott has become a trusted guide for engineers looking to push the performance and longevity of critical metal components. Scott, thanks so much for being with us today.
Absolutely. Thank you for having me.
All right, so tell us a little bit about this S3P Kolsterising process, how it's used, how it's different from competing technologies out there.
Yeah, so the simplest form of what it actually is a thermochemical carbon-based diffusion process designed specifically for stainless steels. I think traditionally, stainless steels have been great for corrosion-resistant applications, but they have their natural drawbacks. Those would be galling, wearing, fatigue, and cavitation erosion. And so this technology is specifically designed to accommodate or overcome those common issues on stainless steel parts and products.
How does the process work?
So what would happen is you would create a finished component, or an end user would create a finished component. They would send that component to my facility in Ohio and North Carolina. I would process it with the Kolsterising technology. We inspect it, pack it back up, and ship it back to you.
Now, I first heard of this Kolsterising process from a friend of mine in the industry. He works at a large medical device company. This is someone who is very, very experienced in engineering, developing hard goods products. He was actually a guest quite a while back on the podcast himself, and he spoke so incredibly highly of this process. He said, for what it does, it is the best process that he has ever worked with. Can you speak a little bit to the physics behind it? I mean, from a physics standpoint, how does this process work? How does it harden the surface?
Yeah. So what is happening in the process is we're using some chemicals and temperature to activate the natural passive layer on the stainless steel. We're then diffusing the carbon into the interstitial spacing between the existing components. So it's being trapped in there and it essentially compresses those components together. We actually see an increase of compressive stresses. And it creates a hardness from a supersaturation of the carbon layer without disrupting any of the mechanical properties. So your tensile strength, your yield, your elongation, they're all completely maintained. We're just putting in some packing material, being the carbon, to compress it all together and keep it all nice and neat.
Okay, so I'm no material scientist or metallurgist, so forgive me if I get some of the terminology incorrect. But what I'm hearing is you've got these molecules of stainless steel, and there's some space in between the atoms, the molecules in this material, and you're just filling that empty space in with carbon so that there's less chance for those molecules to kind of flex in or away from one another. Is that more or less what we're saying here?
Yeah. I mean, that's pretty accurate. Yeah, naturally, you have your existing elements in stainless. You have your iron, your nickel, your molybdenum, and they're all in there, and they're packaged in together with some grain boundaries and structure to the thing. And yeah, we're putting carbon where there isn't anything existing right now, and it pushes those essentially together.
Very cool. Okay. What are some of the problems in other surface hardening technologies that this S3P Kolsterising process solves?
Yeah, so quite often, one of the most common situations that people are trying to address or use the technology for would be coatings. That's probably what we compete against most often. And, coatings are great for a lot of different things, but they also have some natural drawbacks. A lot of coatings tend to add dimensions. They have to build up on a surface rather than penetrate like a diffusion process, like our process does. Additionally, coatings tend to have the hardened layer be consistent throughout so they can be brittle. You have an extremely hard layer on top of a soft base, and then upon impact, it can crack or delaminate or chip in some way, where the Kolsterising also doesn't do that. Sometimes it requires pre-polishing or post-polishing to get a finish that you might like or a finish that will properly adhere the coating to. And then you can't bend it or flex it. Some other heat treatments can sometimes also be applied to stainless. Sometimes nitriding is applied to certain grades. The biggest drawback on something like that is it's a high temperature process. Once you start pushing over 1,000 degrees Fahrenheit, you run the risk of creating chromium carbides or nitrides, which deplete the chromium out of the stainless steel and lower the corrosion resistance. Additionally speaking, when you start putting parts against some high temperatures like that, you run the risk of distortion or warping as well. And you don't have any of this as well with the Kolsterising because it is performed at a low temperature.
I'm gonna admit to not fully understanding the meaning of a word here. Kolsterizing. What does kolsterizing actually mean? What's the technical definition of that word?
So, Kolsterising is the name of the process that we implement. Our group is referred to as the S3P group within Bodycote, specialty stainless steel process, three S's and a P, and the technology underneath the envelope is called Kolsterising. It was named for a man named Ben Kolster in the 1980s who developed it in the Netherlands.
Hmm. Got it. Okay, cool. So this Kolsterizing process sounds like it's pretty generally applicable to stainless steel for, whatever application might benefit from it. Are there particular industries or applications where you've seen this just be like a no-brainer, or is it just, across the board used all over the place?
I mean, you raise a good point, Aaron. People are using stainless across multiple markets, and really, if you have one of those issues, it can be applicable for you to alleviate those issues. That being said, certain industries definitely either require more critical, application or performance, or are using grades of stainless that don't have another solution. Like in the medical and food industry, there's quite a bit of austenite 304, 316, and there's not really good solutions for that grade outside of this process. In areas like oil and gas, you see a lot of exotic alloys like Inconels and Hastelloys where they're investing in those grades, so they really want to keep their investment protected, and so it's a nice solution for those. We actually will be heading to SHOT Show again in January, and the firearms industry is an interesting industry as well for this process because of the distortion of nitriding or the not wanting to do a coating and those sort of things. But I mean, we're in everything from food and beverage, medical, pump and valve, automotive, firearm, oil and gas, chemical, you name it. If they're stainless, you probably have an issue, and we can help you with that.
Cool. Okay. Um, uh, of course, the answer is going to be it depends on the part, I'm sure. But generally speaking, how does this process compare with competing processes from a price standpoint? Is it less expensive? Is it more expensive? Is it roughly the same?
I would say it's somewhere in the middle, maybe middle to high range. We tend to be less expensive than something like hard chrome or electroless nickel or diamond light coatings, but it's more expensive than a simple nitriding. To your point, there's not really a fixed price per pound, and it can be application based. But I think as far as the solution is concerned, it's definitely reasonable. Most of the markets I deal with have no issue with overcoming the cost to first the value. We often offer trials that are at a reduced cost or free or are in order to show people the value. Because at the end of the day, I can talk about how great it is all day long, but if it never actually works in your application, it doesn't do you any good. So we actually pride ourselves on offering trials all day long to really show what the process can do for you.
Terrific. Okay. How about volumes? I mean, is this an ideal process for lower volumes, or does it work equally well for higher volumes? Like, how well does it scale, I guess, as volumes increase or decrease for that matter?
It's a batch process. So really onesie, twosie, all the way up to thousands, 10,000s are perfectly okay with me. I'm happy to process any parts. We are running loads in every single batch, every single week. And we're not going to hold back parts if we're not full or something like that. So if you have one component or if you have multiple components, it really makes no difference to us. We're happy to accommodate.
Okay. It's it's nice to hear kind of a general description of an application, but it can be difficult to identify specific applications. I know from my own personal experience when learning about a new process. Do you have any stories that you can share where maybe you are working with an engineering team and the thought from the team was maybe, oh, we need to change alloys because this one isn't hard enough. When really you and your team came in, you were able to identify that actually you just need a Kolsterising process and not a change of alloy.
Oh yeah, I mean, I have countless stories, Aaron. I don't know how much time you have, but a lot of them are quite fun. I was meeting with a beer manufacturer at one point, and meeting with the maintenance engineer, the director of maintenance, and those guys are always busy, right? And so we set the meeting. He comes in the meeting all rushed, throws a pile of fasteners, nuts and bolts on the table in front of me, and says, "How much am I paying you to treat these fasteners right now?" And I said, I don't know, a nickel a piece, something like that. And he goes, man, you kidding me? He goes, you could have told me $25 a piece. He goes, every time I have to replace one of those fasteners for a galling issue, it's $1,000 in downtime.
Wow.
So I said, well, your new price is $25 a piece, but it's okay. So I mean, that's one. Another one, in the food industry, actually, it's a process. A company that is packaging cosmetics and different makeups and gels and creams and that sort of thing. And we met with one of the guys there, and they had a sugar-based scrub that was going to be going through their line, and everybody else said we're not going to make it through one production run. We're going to have to replace the line 3 or 4 times to make it to the run. And he says, I found this process. It's going to work. Trust me. And so we ran some parts for him, some plungers and some dosing nozzles, and sure enough, it made it all the way through the product. Actually, 2 runs of it, and he became a hero at his facility. And the next time we came there, he's walking us around the facility, introducing to this guy. Hey, these were the guys I told you about, and this is what it was. And so, those are fun experiences, and you just get to sort of see behind the curtain of some of these manufacturing sites and some of these applications that you might not have ever thought of before, but really can make a difference for someone.
Yeah, once you show that you can actually solve a problem for someone, those doors tend to open wide open.
Oh yeah. Oh yeah.
Uh, Um, I backing up a little bit, looking at this a little bit more high level, are there like common misconceptions that you've seen engineers typically have when it comes to hardening stainless steels, or does everyone out there just know exactly, everything about it?
Oh no, not at all. A lot of what I do is educating. I mean, from speaking to classrooms of engineers to walking in a site that I've done business with for a decade and raising my hand and saying, "Who here knows what Kolsterising is?" I'll have a room of 10 engineers all shake their heads. And I'll say, okay, well, why are you using it? And they say, well, it's on the drawing. And I'll say, well, who wrote the drawing? And they're like, that guy's been gone for 5 years. And so it's constantly educating and re-educating that exists. So I mean, people don't believe you can harden stainless steel because if they've tried to do it by traditional heat treatment methods, they've destroyed it, especially like I said, austenites or duplexes. So they don't believe it can happen. Two, they don't typically believe I'm getting as hard as I actually can get the alloys, which is around 70 Rockwell C, which is
Wow.
incredibly hard. Three, they hear, carbon, and their first instinct is, "Ooh, what's happening to my corrosion?" Are you rolling the corrosion or destroying the corrosion? Because, if you add carbon to most things, it's going to turn into a rust type situation. And so we have to sometimes prove that or show that. And then the last is embrittlement. People hear 70 Rockwell C and they think, oh, it's gonna crack. And it actually doesn't. It actually bends and moves because it's hardest at its surface and gradually reduces within its own layer back to the base metal. So those are the things we have to overcome. And then, of course, just naysaying. Engineers love to touch and feel and believe and see for themselves. And again, that's where the trialing comes in to really show them that it does what we say it does.
Yeah. Do you ever, or do engineers ever replace like tooling steel with a Kolsterized piece of stainless steel? I mean, does it get that hard?
I've had that situation before. It can be hit or miss though, because generally speaking, A2, D2 tool steel is pretty inexpensive. It's pretty hard. And so, some from a cost perspective, it might always make sense to go to a stainless steel tooling application. But I have had it done, especially in the automotive industry where they need a non-magnetism, and they chose a 304 or 305 alloy for that reason. Recently, they've been doing some dies for extruded elements in aerospace, which has proven to be incredibly successful in that industry as well. So definitely see some tooling, but a lot of times if you've chosen tool steel, you've chosen it for a reason and you don't need the corrosion, so it doesn't make sense necessarily to go somewhere else.
That makes sense. Does it work equally well across different alloys of stainless steel? 303, 304, 316, 420?
Generally speaking, the hardness profile is the same. We can get around the same hardness level on all those. Where you see the difference between some of the alloys will be your average case step. So, an Inconel won't receive the carbon the same way an austenitic will. A Maranging, 300 receives the carbon very well, even more than that austenitic did. Martensitic alloys don't receive carbon in the same way without the addition of nitrogen, so they need a slight modification on the process in order to get a proper diffuse zone. So the alloy will sometimes dictate some changes, but for the hardness profile, they're almost all identical around that high range.
To what extent is your team still developing or improving applications of the Kolsterising process, or is it, the process is pretty much set at this point. It's never going to change. You get what you get, and that's all what it's going to be.
We are constantly trying to innovate and get out ahead of things or taking customer feedback and trying to accommodate an additional solution or trying to be more proactive and dynamic. Some examples of that are an increase in our size envelope, being able to process bigger parts. That's been something we've developed over the years. We were getting feedback. I don't know if you've ever worked with austenitic cold work fasteners. Sometimes they'll cold work the fastener from some mechanical properties. Well, if you do that to an austenitic alloy, sometimes you can create deformation martensite, which has lowered the corrosion of the grade. And you can tell if you've done that by putting a magnet to it. If it has magnetism, then there's martensite there. Well, the Kolsterising process we found can sometimes speed that reduction of corrosion up on those particular cold worked fasteners. And so we actually developed a technology to accommodate that, where you sacrifice a little bit of the hardness, a little bit of the depth, but you don't see that speed up of the lowered corrosion on those particular things. So that's been something we developed over the years. Things with our cleaning line, just being more efficient, being more clean. Yeah, we're always looking to do testing or another lab setting or working with universities to discover other additional benefits or value add. We recently worked with a educational system in France where they were studying hydrogen embrittlement. In some ways, the automotive industry, hydrogen compression engines might be the future. And so we were working with a lab and we discovered that Kolsterising actually reduced hydrogen embrittlement by nearly 40%.
Wow,
Uh, yeah, so yeah, we're constantly looking at the next thing and the next direction we can go.
nice. You had mentioned the size of parts that you're increasingly able to accommodate larger part sizes. What's the current range of part sizes that this process will accommodate?
So the basket itself is about a 20-inch diameter by 23-inch tall cylinder right now. So that's sort of our size envelope. We are bringing a bigger unit to the United States. It's actually being installed right now in my Mooresville, North Carolina facility, and it can accommodate 4-foot diameter but up to 6-foot long parts. So a
Wow,
significant size envelope increase.
huge increase.
Yes, sir.
Oh man, what drove that? I imagine there are some specific applications that drove this dramatic size increase. Can you talk about any of those?
Well, we actually had the technology. We've had it in Germany for a while, and as a U.S. person who is responsible for, illustrating what this brings to the market, we've always said places in oil and gas, especially, need that bigger size where their valves alone, can be over 2 foot, be over 4 foot. And so once we started to develop and gain more traction in industries like that, the need to have the bigger size has just become more and more evident.
Got it. Okay, that makes sense. Um, are there any other like specific stories or applications you can think of where maybe the Kolsterising process solved a galling problem or like a wear problem? Any other examples that you can share to help spark in the minds of those listening to this? Oh, I could use it for, for this project or for that project.
Yeah, so working with a medical company that we've been doing business with as long as I've been here, I finally got the opportunity to meet the individual who actually had developed the Kolsterising process with their company, and he told me this story. He said that they were working with suture cutters, where they were looking for a tool that could tie off and cut the suture cleanly during the surgery, and without having any burrs or brays or a fraying of the suture or the line itself. And they had tried 400 series martensitic stuff. They had tried 17.4 in an H900 condition. They had tried all the traditional things to try and get a hard but corrosion resistant stainless blade to cut the suture cleanly. And their goal was to get to 6 clean cuts. Six, when you think about it, that's not very many, right? When you think about it. And they were getting to 4, they were getting to 5, they were getting to 3, and just never were able to get to 6. And finally, he found Kolsterising. And not only was he able to switch to a 304 alloy for more corrosion resistance, but after we treated it, we got consistently to 60 cuts without any
Wow.
issues.
60,
So
60?
6 0. So he
Wow.
never looked back. Never looked back after that.
See, that's really interesting because I'm not very familiar with this process, and I've been thinking of it as kind of like, I don't know, chunkier, blockier parts, but thinking of it as a blade. That's a pretty delicate, precise instrument that I hadn't even thought about before. So, uh, edge treatment on a blade is a good application.
Oh, absolutely. With it being a diffusion as well, you don't round off the edge. If some coatings need to adhere to a flat surface, and they'll round an edge on you. In the poultry industry, we're also seeing a good deal of success on 304 blades. Again, they were using martensitic alloys. What they were seeing was an embrittlement of the blade that would sometimes create chipping. So they're having to throw product away and replace the blades. We got them to switch to a 304, added Kolsterising in. They went from a 2-hour PM maintenance schedule to a 2-week PM maintenance schedule on a blade and eliminated the chipping issue.
That's fantastic. Okay, so you had mentioned earlier that one of the challenges you've had is just convincing engineers that this actually works. Like it does what I say it's going to do. And that can be tough because I know myself included, engineers are skeptical and we are very risk averse and we want to see proof that this thing actually does what we're being told it's going to do. What has your team been able to do to help like just prove the process to engineers?
Yeah, so we have data. We have general data that we typically present. When we meet with a group, we usually will give a technical presentation that includes some of what we've talked about, some slides and some imagery of the process itself and what we're actually physically doing. And then sort of the back half of the presentation illustrates the benefits and standardized tests that we've done that illustrate those. So an example would be the G98 button test for galling. We show the galling threshold in that particular certified test. We also have a video. If you go to YouTube and you search Bodycote Kolsterising galling, you'll see a video of a technical manager in Germany illustrating anti-galling properties on some samples. We have wear test, taper abrasion wear test, the ball on disc wear test that we illustrate and show the data surrounding our performance in those tests, bending, rotating, fatigue tests, as well as a comparison to springs directly against shot peening, in fact. And then ASTM G32 anti-cavitation test are some of the illustrations that we show, just to get the ball rolling. And then, of course, we have the conversations about their particular applications and sometimes able to illustrate like examples where I knew we were successful. But at the end of the day, really, it really comes back to give me a part, let me take it with me, let me treat it for you, and then you put it on your equipment, put it on a test stand, give it to an end using customer, and let them tell you exactly how great it was. And that works more times than not.
Yeah, yeah. Are there applications where one might think that S3P Kolsterising would be a good fit, but actually, there's a trick here. That particular application, no, that's not a good fit. Are there any, gotchas like that that you can think of?
Oh yeah, I mean, like any other solution, it's good a lot of the time, but it's not perfect for everything. One thing would be like an anti-leaching. Some coatings are designed to be self-lubricating, so like a Teflon, where they don't want the stickiness. In those circumstances, I'm not the ideal application like that. It's a difference between if it's something is wearing and embedding versus sticking, but typically my instinct would be, all right, I'm not going to be best there. Also had a customer one time. He was doing a pump rotor, and he said nothing is working on it. And I said, okay, well, what are you pumping? He goes, I'm pumping a sand slurry, about 90% sand. And I said, oh, okay. I said, well, we'll give it a shot, but well, I don't know how well this is gonna go. And so I treated parts to send them back to him, and sure enough, it lasted 10 seconds or whatever before he sandblasted the thing off. And so
Yeah.
yeah, that wasn't ideal. High heat, anything that is pushing temperature ranges into 1,000, 1,200, 1,300 F for extended periods of time may not work out. You might see a further diffusion of the carbon into the alloy and just basically lose the benefit, but not create any adverse effect. Just lose what you're trying to do. So those would be the ones that I would say maybe not ideal. I have had some people push the temperature range in suppressors and different mechanical seals and that sort of thing, and we have shown performance there, but we typically say stay at 1,000 F and under. You're gonna be good, but those are
Got it.
those.
That's really helpful to hear. Um, do you see, like, I don't know, looking into the next 5 years or so, are there any new or emerging applications or industries where this is going to be a great fit? I know that you and your team, like you mentioned, are always innovating, trying to improve the process. Any, big leaps in the technology or new methods of applying it that we can look forward to? Not that the applications right now are, limiting at all. It sounds like there are already so many different ways that an engineer could use this, but anything new opening up over the next several years?
You know, um, I don't think so. Like getting a big size is going to be a big one for the U.S. That's
Yeah.
brand new, right? That's supposed to happen Q1 here, so that'll open up a lot of doors for us. Some emerging markets though that we're seeing success in that we haven't been in the traditional sense of what we would approach would be those in space. Seeing
Mm,
rocket applications and cooling systems and those types of applications. And then AI. Obviously, if you're not paying attention to what's going on with AI out there, you're not noticing that it's blowing up.
yeah.
And So we've actually seen some application in the cooling systems for data stacks.
Oh,
And
interesting.
and yeah, so the more processing power that's going to be required to generate all this AI, the more type of technology that you're going to have to keep those things cool and running, and you don't want leaks or anything like that. So some of the tubing, piping, pumping of that type of cooling applications, I think, could be a big plateau for us in the next couple of years.
So you clearly know your stuff when it comes to surface treatments. You've spent a career developing that knowledge base. For engineers who are listening to this that, maybe aren't as far along as in their careers as you are, uh, any tools or resources that you can recommend for those engineers who want to learn more about surface treatments? The internet is full of resources and different things out there, but anything in particular that you recommend?
Yeah, I mean, I think a lot of companies, mine included, are more and more offering educational webinars. I know that's a big focus for us going into 2026 is to say, hey, if we can't get to you or you're not going to be in the area where we're traveling in, here's something online that you can just participate in for 15, 20 minutes and really get a good grasp for not only what this is, but some of the things it competes against. And I think that's a generally a good resource for people. Google can be a little bit of a miss, ironically. I've Googled certain terms and not been able to find what I wanted. So don't always trust Google. Some of the message boards can be good because I think generally speaking, the people who post on there want to truly help and offer suggestions and solutions to things that you may be dealing with. But of course, reach out to Bodycote. Whereas I only focus on this particular technology, I'm happy to pay liaison to other activities that you may be doing or issues you're trying to resolve. Bodycote does have other coatings and other divisions, multiple heat treating options, including some proprietary stuff outside of this technology. So there's a lot of metallurgy and engineering information within my organization that we're happy to share and help educate people.
Terrific. What is the best way for engineers to reach out to you?
They can reach me via email at scott.roberts, Roberts, at bodycote, BODYCOTE.com. You can find me on LinkedIn. I'm a pretty active user of the LinkedIn platform. Call me on my cell phone, 316-633-2362. And of course, you can go to the Bodycoat website and you can fill out an inquiry. But if you reach out directly to me, it's going to come much quicker than through the system that has to flow through some audit trails and everything like that. But yeah, if they need me, feel free to reach out. It bothers my family, but I typically have this thing on me and I'm typically looking at it. So
Well, first of all, thank you to your family for being so supportive of that. I know that it is such a huge benefit when I can reach a company, quickly and directly. There was an application that we were working on recently. I was mostly working on quoting a project, and it required a pretty specific glue dispensing technology. And there's this large glue dispensing company out there. I won't say the name of it, but I spent, no joke, 3 weeks trying to get in touch with the right person at this company. And I filled out forms on their website. I called phone numbers. I got passed off to this person and then that group and then that group and this person. And it literally 3 weeks of this. And I still never got in touch with the right person. I finally threw my hands up and said, forget this. I'm moving on to someone else. So, the fact that you're willing to share your cell phone number on this podcast is huge because that can often mean the difference between a company like mine finding a solution in a tolerable timeline and just being incredibly frustrated and missing timeline. So thank you for
yeah,
being so open there.
absolutely. I mean, our time is so valuable, right? And so if you're chasing something for so long, eventually you're going to raise your hands and say, forget it. Like I got better things I can do. I got more
Yep.
valuable things I can do. And so I pride myself on trying to reply to everybody within 24 hours unless it's Christmas or something like that, right? Coming up. But
Yeah.
at least I'm going to get back to you and tell you I'm working on it, or I have a solution, or put you in touch with the right person. It's just the way we operate. So.
That right there is huge. All right. Well, Scott, anything else that you'd like to share that we haven't touched on yet about the Kolsterising process or body coat in general?
No, I don't think so. I mean, yeah, if there was a question that somebody has, please don't hesitate to reach out. We like questions. Questions are great. It provides a dialogue and encourages a dialogue. And I say this to all the time to people I work with. We love to do these types of podcasts. We like to do educational sessions because at the end of the day, yeah, we're in a business, but we're really looking just to be partners with people. The more successful that I can help you grow, alleviate this issue, whatever it might be, the more successful I'll be as well. So we're a solution provider, and that's what we're looking to do. I'm not getting rich. I'm here. I've been here for a while. I keep playing the Powerball, but that doesn't seem to work out. I'm going to continue to be here, and I'm going to continue to work with people and help them, get rid of their nightmares.
Excellent. All right. Well, Scott, thank you so much for sharing all of this knowledge and wisdom today. Some really specific and useful information that hopefully engineers can take and use for their surface treatment projects, surface hardening projects. Appreciate your time, and we'll look forward to getting this out there and sharing it with the community of engineers.
Very good. Thanks again for having me.
I'm Aaron Montcur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.